So, we shall now consider the next topic of interest to us in this course, namely numerical differentiation. So, given a set of values of f of x, say at x0, x1, etc., xn, the question is, can this information be used to estimate the derivative of f at some point, say C? This question is answered in numerical differentiation. The answer is yes. There are a number of methods which we would now develop, with the help of which we will be in a position to present an estimate of various order derivatives of this function, whose values are given at a set of points, say x0, etc., xn. So, we know from the definition of the first derivative that f dash of x is limit as h tending to 0 of f of x plus h minus f of x divided by h. So, this definition is such that a formula for numerical differentiation emerges from the above definition, namely f prime x is approximately f at x plus h minus f at x divided by h. So, the right hand side gives you an estimate of the derivative at the point x. Suppose, say, f of x is a linear function a plus bx, and let us see what this formula tells us. Suppose I call this as star, then left hand side of star is f dash of x, and that is b. I compute the right hand side of star for this function. So, it is f of x plus h minus f of x divided by h. So, it is a plus b into x plus h minus a plus bx divided by h. So, that gives you bh by h, which is b, and this is the left hand side of star. So, the formula is exact for a linear function or a linear polynomial. So, we would like to see the expression for the error that is incurred when we use star to estimate the derivative of a function. So, let us compute the error in this approximation star. So, to do that, let us evaluate f at x plus h. Use Taylor series expansion. So, this will give you f of x plus h f dash of x plus h square by factorial 2 into f double dash of x plus etc. Suppose I truncate this at this stage, then this will be f double prime at psi, and f at x minus h is going to be f of x minus h into f dash of x plus plus h square by factorial 2 into f double dashed, say at some other point psi 2. Let us use the result, say 1, in writing what f dashed of x is. So, f dashed of x will be f of x plus h minus f of x divided by h minus h by 2 into f double dashed at psi 1. So, this tells me that I can approximate f prime x by this term, which appears as the first term here, and that the error that I incur is given by this term, which is h by 2 into f double prime at psi 1. In order that the approximation of f dashed of x by star is valid, when I use 3 to approximate it, we require that the function f prime are continuous in the interval x to x plus h, and that f double prime exists in the open interval x to x plus h. So, the error term which consists of these two factors h by 2 and f double prime tell us to what class of functions that f must belong to, so that I can estimate its derivative by the formula star. Namely, this term tells us that f must be such that if it belongs to the class of functions where f prime are continuous in x to x plus h and f double prime exists in the open interval x to x plus h, then I can estimate the derivatives of all functions belonging to this class by star. Namely, the first derivative can be estimated, approximated by the expression on the right hand side in star. Then what about this factor h? That tells me that what happens as h goes to 0? H goes to 0, the error term goes to 0. So, this gives me the order of accuracy of the formula that is used in the estimation. Namely, the power to which h is raised to gives you the order of accuracy of the method, and therefore, the method 3 which can be used to estimate f prime x in the interval x to x plus h is of order of h. So, the error in 3 or error in star is given by the term here in 3, and it is of order of h. So, having obtained a method or a numerical differentiation formula which directly emerges from the definition of the first derivative, we would like to obtain some more numerical differentiation formulas. So, let us now use result 1 and 2 and see what we get. If suppose I take 1 and 2 and add, then f of x plus h plus f of x minus h, then minus twice f of x divided by h square is f double prime at x. So, I have a numerical differentiation formula for the second derivative of x, so that if x is here, then x minus h and x plus h are symmetrically located about the center point x, So, if I want the second derivative at this center point, then it can be estimated by the values at the points which are symmetrically located on either side along with the value of the function at this point given by the expression on the left hand side. Here again we can compute the error in such an approximation, and that can be done by writing down the next term here. So, let us do that and write down the error in this approximation. So, f of x plus h is f of x plus h f dashed of x plus h square by 2 into f double dashed of x plus h cubed by 3 into f triple dashed at x. I shall write down one more term, you will see why we do it, the fourth derivative at x, and I am going to truncate here. So, this will be the remainder term. What is f of x minus h? It is f of x minus h f prime of x plus h square by factorial 2 f double prime of x minus h cube by factorial 3 into f triple prime x plus h power 4 by factorial 4 into fourth derivative at say some psi 1 at some say psi 2. So, now what did we do? We added the 2, so and that gave us f of x plus h minus twice f of x plus f of x minus h. So, we observe that when we add, this term cancels with this, and then when we add we get h square f double prime x. So, I divide by h square, and then when we add, these two terms cancel, and these two terms, right, give you minus h power 4 by 24 into the fourth derivative at psi 1 plus the fourth derivative at psi 2, and that is f double prime at x. So, you have f double prime x to be estimated by the first term, and the error that is incurred in such an estimation is given by the term which is this. Remember, we had divided by h square, and so the term here will be h square. So, the error is of order of h square, and you now can give the class of functions which can be approximated, I mean whose second derivatives can be approximated by this formula based on the error term. Namely, it involves the fourth derivative, and the factor which involves h square tells you that the error is of order of h square. So, let us try to see how we can present this error term. So, it is the fourth derivative at psi 1 plus the fourth derivative at psi 2, which should be now expressed in such a way that we make use of some properties of the function that we have considered. So, we assume that the function belongs to a particular class such that the fourth derivative exists and is continuous, where on the interval x minus h to x plus h, and let capital M and small m denote the maximum and minimum of or minimum values of this fourth derivative on this interval x minus h to x plus h. Then we know that the fourth derivative at psi 1, fourth derivative at psi 2, and the fourth derivative at psi 1 plus the fourth derivative at psi 2 by 2, let us call this as some c, they all lie in the interval small m to capital M, because m and m are the smallest and the largest values of the fourth derivative on this interval. So, these lie in the interval m to capital M, and since this fourth derivative is continuous, it assumes the value c at some point, say psi, which lies in the interval x minus h to x plus h. So, hence f fourth derivative at psi is c, which is half of the fourth derivative at psi 1 plus the fourth derivative at psi 2. And therefore, now we can give the numerical differentiation formula for the second derivative in terms of what we have obtained. So, f double prime at x will be f of x plus h minus twice f of x plus f of x plus h by h square, then minus h square, fourth derivative at psi. So, this gives you a numerical differentiation formula for f double prime x, where psi lies between x minus h and x plus h. So, one can use Taylor expansion of the function at different points like x plus h, x minus h, etc., and obtain various numerical differentiation methods involving, say, 2 points for f prime x, 3 points for f double prime x. And you can also obtain a numerical differentiation formula involving more number of points for estimating f prime x, and similarly for estimating f double prime x or higher order derivatives. F prime x can also be obtained using the estimation f at x plus h minus f at x minus h by 2h, and the error involved is minus h square by 12 into f triple prime at psi 1 plus f triple prime at psi 2. And by arguing out in a way similar to this, while deriving an approximation for f double prime, you can show that f prime x can be estimated using the first term in this formula, and the second term is minus h square by 6 into f triple prime at psi, where psi lies between x minus h and x plus h. So that the truncation error in this case is of order of h square. And you observe that while the truncation error in this method is of order of h, in this method you are able to get the truncation error to be of order of h square. These are called forward difference approximations for the derivative, and this is called a central difference approximation for the first order derivative, because the derivative at the central point x is approximated in terms of the values of the function at x minus h and x plus h here, whereas here the derivative at any point x is given in terms of the values at the function, values of the function at a point which is x plus h, and it also involves the function value at x. So, one can also derive a backward difference approximation to the first order derivative, and that will be given by f prime x is equal to f of x minus f of x minus h by x with the error term which will be similar to this expression. So, we shall now consider numerical differentiation methods which can be obtained in case we are given the set of information about f at points which are equally spaced. The method is known as the method of undetermined coefficients.